Hey, what's up everyone? This is the last video for the Pinterest on-site interview 2020. This one is a really simple one, so let's get right into it. The interview question was, given a list of bad phrases and a query, detect whether the given query contains any bad phrases. Let me give you some examples. Here are the bad phrases, hate you and hatred. And let's go through the following three query to understand what the algorithm should output. The first query, oh man, I hate you. It should output true because hate you is included. It's a bad phrase. Let's look at the second query. I love you. The output should be false because it doesn't include any of the bad phrases within the query. The third one, I hate you, comma, but I love you. It should output true because it still contains one of the bad phrases right here. Now pause the video and try to solve this question. It's a pretty simple question, so it shouldn't take you long. In this video, I'll go over the brute force approach, optimized solution using Trie, and how to code both solutions. The brute force approach is pretty straightforward. You just need to iterate through each bad phrases and see if it's contained in the given query. It's like 5 lines of code. So given the list of bad phrases as a string array and a query, you just need to iterate through the bad phrases and use the query that contains method to see if any of the bad phrases included in the query. If that's the case, you return true. Otherwise, you return false. But does it actually work though? It works for most cases, but it would miss some edge cases. Let me give you an example again. Let's say we have the following inputs. Hate you and hatred, same as before. With the previous brute force code we have, it will output true for this query, hatred hyphen not, because hatred is included in the query right here, right? It will match. But the hatred was connected by another word with a hyphen. So the algorithm is supposed to output false in this case, just for the sake of this interview question. So we need some additional checking to make sure that the standalone phrase is included in the query, not just part of it. So let's just move on to the optimized solutions, and I'll show you how we can catch such cases. The logic is similar for both brute force and the optimized, so I'm just going to explain it there. For the optimized approach, we'll use trie. So for each letter you see, you're constructing a node. So for us, bad phrases are hate you and hatred. So we're going to start from hate you. So starting from the root node, you're creating a node for H, A, T, E, and a space and a U. When you reach the last letter, you mark the node as a leaf. And for the second word, H, A, T, and then you have R, E, D, and that's the last letter, so you also mark that as a leaf. All right, so after we construct the trie, we will iterate through the query and see if the query contains any bad phrases. So for this algorithm, we'll start with index 0 from the query, which is right here, O. And whenever we fail to find bad phrase at a certain starting index, we'll start the search from the next word. So if we fail from O, we're going to go to M and start the same algorithm again. If we fail from M, we're going to start from I. And if we fail again, we'll go to H, and we'll iterate that algorithm until we hit the last word within the query. Okay, so let's go through this example here. So when we start from the index 0, O, the root node doesn't contain O, so we skip, go to the next one. M, same thing. I, same thing. But when we start from here, H, we go H, A, T, E, space, and U. And then there's a leaf, right? So we can tell that the query contains a bad phrase. And similarly, let's look at the second example. So the trie is the same, but the query is different, hatred not. So when we start from the index 0, it's going to go H, A, T, R, E, D, right? And it's a leaf node. But here, we need to do additional checking that like it's right here, but the next word is either a space or comma or a dot, not a hyphen or any other words. So in this case, We reach the leaf here, but the letter right next to it is not a space or a comma or a period. So we skip this and continue. But when we try to continue, there's no other words, so we fail. But when we try to go to the next word, there's no next word, right? It's just a single word query. So the algorithm is going to input false in this case. So the time complexity for this algorithm can be order of W times L, where W is the number of words within the query and L is the length of the query. So the worst case, you might have to iterate through the entire query for the number of words because that's how many iterations you do. So depending on the input, this tries approach perform better compared to brute force or vice versa. But in average, this approach should perform better. All right, let's see how we can implement this in code. So here's the function signature. It returns a Boolean value and the name is contain bad phrases. And we have two inputs. One is the bad phrases and one is the query. All right. So first thing first, we're going to construct a trie with a given list of bad phrases. Instantiate trie and go through the bad phrases and insert it into trie. We'll go over the insert logic in a bit. Then what we do is iterate through the query and see if it contains any of the bad phrases. And we're going to use this index variable to keep track of the starting point. So we're going to start from the index 0. And on the index 0, if we can't find any bad phrases, then we'll update the index to the next word. So how we do that is we find the index of the next space by using the index of method. All right. One thing to note here is that on the first iteration, we don't need to update the index because we know it's going to start from 0. But on the next iteration, we need to do index plus 1 because this index of method returns the index of the space. So we need to increment the index to start searching from the next letter, not from the space. Otherwise, you will get this infinite recursion. All right. And we'll go over the implementation of contain here. But if this returns true, then we return true because it means the given query, whatever the starting point is, it's containing the bad phrase, so return true. Otherwise, we continue the iteration. And after we iterated through all the starting point and we couldn't find any bad phrases, then we return false here. And let's look at how we define the trie node here. So just have a map of character, children. So key is a character, like the letter, and the trie node is like the nodes that are connected to this character, right? And we use this variable to indicate whether this node is a leaf node or not. And if you look at the trie, like the insert method, what we do is we start from the current node, the root node, and we iterate through all the letters on the given phrase, and we try to construct the trie. So I use the method called compute if absent because it's like the most concise. But what it pretty much do is, given a key, if this key, like the letter, does not exist in the map, it will call this method to create a new key value pair with this letter as a key. So if the letter does not exist, I'm just going to construct a new trie node and just insert it in the map. And so once we iterate through all the letters, we just mark the final leaf as a leaf. And the final node as a leaf. Okay, and this is the most interesting logic. The contain method. It's the same thing. We turn the query into a letter, the character array, and we start from the root node. And here, we just iterate through the trie. So if the children does not contain the current letter, then it means we don't have any word does not exist. We know for sure that the given query does not exist in the trie. All right, so we return false in this case. But if you found a word matching part of the given query, or here, if you found the word, not the word here, phrase, matching part of the given query, then we return true. How do we tell that? So first, we check whether it is a leaf node, and if the current index I+1 is a letter dot length, it means it's the last letter of the query, right? So we know this is a word, not like connected by hyphen, all right? And another thing we can also check is whitelist characters dot contains. So what whitelist characters contain is a period, comma, and a space. So if the next letter is a comma or period or a space, it means it's not connected by any other letters. So we know it is a complete word or phrase, so we return true in that case. Otherwise, we'll just continue the iteration by setting current node equals to node, right? And once we iterate through all the letters and we can't find the bad phrase, like we don't hit this either return true or return false case, then we return false here. All right, we're done. I would be interested to know how you would code this as well. If you have any questions or different approaches in mind, feel free to comment below and let's discuss. Also, I included the full solution in the description, so check that out as well.